Hello everyone, welcome to my class. In today's class I am going to cover Lagrange multipliers, which is also called lambda method, to find the maximum and minimum of functions. So let me start the class right away. In our last class we mentioned there are two types of optimizations. One is constrained optimizations and another one is unconstrained optimizations. And we covered unconstrained optimization in previous section 14.7. So today we are covering the constrained optimizations. In constrained optimizations, we used to find the extreme values of functions subject to some constraint curve given of the form h xy equals to k. So for example, in the diagram here, we have the upside down paraboloid. The maximum lies here, which is unconstrained maximum. But if we restrict the domain or xy coming from this curve, then its maximum lies here. So the unconstrained maximum and constrained maximum are different values. So the mathematical setup, we want to optimize the functions f of xy subject to constraint where xy satisfy this equations h equals to k. Sometimes the f is also called objective functions and h equals to k is called constrained equations. So let's talk about Lagrange multipliers or the lambda method, the ideas. In geometric terms, let me go back again to this diagram. So this constraint curve touches some level curve of this surface, and at that point of tangency, the tangent vectors at constraint curve and at level curves are the same. So in geometric terms, the constraint curve touches some level curves of f at a point, so they have a common tangent line. This implies their gradient vectors are parallel, and we know two vectors are parallel if and only if one vector equals to constant times the other vector. So here is a gradient f is parallel to gradient h, implies gradient f equals to some constant times the gradient h. We pick that constant is a lambda, and that lambda is called the Lagrange multiplier. Next, our goal is to find all point xy which satisfy the system of following equations. So here, gradient f minus lambda times gradient h equals to 0, and the constraint here, h minus k equals to 0. It's a system. Now we want to solve these systems. Solving this system is sometimes tricky. One way is by writing it as a single function or equations called the Lagrangian functions, defined by L xy lambda. So L is for Lagrangian. Xy lambda equals to the objective functions fxy minus lambda times the constraint, fxy minus lambda times hxy minus k. Sometimes people make mistake here. They sometimes write the constraint and then minus lambda times the objective functions, but that doesn't work. So always we define the Lagrangian function in this way: objective functions minus lambda times the constraint here. I hope this makes sense to you all. So now our goal is to optimize these Lagrangian functions. And our idea, first find the critical points. To find the critical point, find the partial derivative of L with respect to x, with respect to y, with respect to lambda, set equals to 0. Find the value of x, y, and lambda. But in this method, we don't care the value of lambda. Then using the lambda's value, we find the value of x and y, and we evaluate the function at x and y. Great. So the first find the critical point. So find the partial derivatives and of L functions and set equals to 0. Then this gives us this equations here. So we do have this system equation here. Fx equals to lambda hx, fy equals to lambda hy, and hxy equals to k. So next, solve the system of for the point xy and evaluate the functions at those points. Quick note about this idea here. In the above system of equations, there are 3 equations and 3 unknowns. Here you have 1 equations, 2 equations, 3 equations, and we have unknowns are x, y, and lambda. But we don't actually care the lambda. So first solve the systems for lambda in terms of x and y to get rid of lambda from the equations, and then get all the points xy satisfying the system. Finally, evaluate the functions at those points and conclude that the biggest value of f will be the maximum value of f, and the smallest value will be the minimum of f subject to given constraint. Great. So with this idea, now let's do some example. Let's move on. Example 1. Find the extreme values of the surface. Here fxy equals to 4x square plus y square. It's a paraboloid, by the way, on the unit circle where x and y satisfy this equation, x square plus y square equals to 1. So here this is our f of xy and this is our hxy, which is k. K is 1 here. So let's begin the solutions. Define the Lagrangian functions. L x y lambda equals to objective functions minus lambda times the constraint. Here x square plus y square minus 1, and this is the fxy, and this is the lambda. So next, let's find the critical point. Find this bunch of partial derivatives. Find Lx. Lx equals to, here's 8x minus 2 lambda x. Keep in mind that we are taking partial derivative with respect to x, so y's are constant. Set equals to 0. Simplify. It gives us here's either x equals to 0 or lambda equals to 4. By the way, we don't care the lambda value. We only care x equals to 0. In the second line here, the partial derivative of L with respect to y is 2y minus x squared 0, 2 lambda y, so minus 2 lambda y. Set equals to 0. Simplify. It gives us y equals to 0 or lambda equals to 1. Again, we don't care lambda value. Third line here, take the partial derivative L with respect to lambda. So that means x squared times 0, y squared times 0. So only here. So that means x squared plus y squared minus 1. X squared plus y squared minus 1. Set equals to 0. I mean, here I forgot the minus sign. I have to multiply by minus, but when you are setting equals to 0, that minus disappears. So we have x squared plus y squared minus 1 equals to 0. This implies x squared plus y squared equals to 1. I hope this makes sense to you all. So the next, so let's find the value of x and y. Means put x equals 0 in this equations, put y equals 0 in this equations. So if x equals to 0, the last equation gives y equals to plus minus 1. And if y equals to 0, again the last equation gives x equals to plus minus 1. So we have the critical point when x is 0, y is plus minus 1. When y is 0, x is plus minus 1. So we have 4 critical points. Next, let's evaluate the functions at those critical points. So here's f at 0 plus minus 1 gives us, it's our function here, fx squared plus y squared. So 4, this is the x value, this is the y value. Simplify gives us 1. Similarly, evaluate the f at this critical point, which gives us 4. So that means we found the maximum is 4, minimum is 1, maximum at these 2 points, minimum at these 2 points. So the maximum of f on the circle is 4. at this point, plus minus 1 0, and minimum is 1 at this point, 0 plus minus 1. I hope this computation makes sense to you all. So actually these values correspond to the highest and lowest point on the curve, where the curve consists of those points on the paraboloid that are directly above the constant circle. So on this curve, which is just above this constrained circle, we have the highest point is 4 and the lowest point is 1. Great. I hope this idea makes sense to you all. Now let's move on. Example 2. Find the extreme value of functions f equals to 6xy. The constant curve is the ellipse. 3x square plus y square equals to 6. Begin the solutions. Just the routine computations. So let's define the Lagrangian functions. L equals to objective functions minus lambda times the constraint, which is here 6xy minus lambda times 3x square plus y square minus 6. Next, found these partial derivatives. L, partial derivative with respect to x, is 6y minus 6 lambda x, set equals to 0. Solve for lambda, gives us lambda equals to y over x. Similarly, Ly equals to 0 gives us lambda equals to 3x over y. Similarly, L lambda equals to 0 gives us 3x square plus y square equals to 6. By the way, always the partial derivative of Lagrangian functions with respect to lambda, when we set it equals to 0, it gives us always the constraint curve. So this is the constraint curve. 3x square plus y square equals to 6 is here. 3x square plus y square equals to 6. In the earlier case also the same. L lambda equals to 0 gives us x square plus y square equals to 1, which is here. That's the idea. Great. So let's move on. So then now our goal is to find the value of x and y. Again, we don't care the lambda value. So from first two equations, the same lambda, let's equate these two lambdas. That means equate the right hand side. So y over x equals to 3x over y. Then from here, y square equals to 3x square. And then substitute y square equals 3x square in the third equations. 3x square plus y square equals to 6 becomes 3x square, and y square is again 3x square, so total 6x square equals to 6. Solve for x equals to plus minus 1. Put y equals to plus minus 1 back on y square equals 3x square, then y equals to plus minus radical 3. So consequently we have critical point 1 plus minus radical 3 and minus 1 plus minus radical 3. Again 4 critical point. So next step, evaluate our function at those points. So here's f at 1 radical 3. Again our function is 6xy. 6, x value is 1, y is radical 3. It turns out that 6 radical 3. Similarly, f at 1 minus radical 3 turns out to be minus 6 radical 3. Similarly, f at minus 1 comma radical 3 turns out to be minus 6 radical 3. And f at minus 1 comma minus radical 3 turns out to be 6 radical 3. Therefore, the maximum of f on the ellipse is 6 radical 3 at these 2 points, and minimum is minus 6 radical 3 at these 2 points. I hope this makes sense to you all. Great. Let's move on. Let's do for function of 3 variables. Example 3, optimize the function of 3 variables, which is 2x plus 2y plus a z, and on the sphere. X square plus y square plus z square equals 9. By the way, this is also a level surface. So thus begin the solutions. Define the Lagrangian functions. L equals to objective functions minus lambda times this constraint. Then take this bunch of partial derivatives here. Lx set equals to 0. Then this gives lambda equals to 1 over x, equation 1. Similarly, partial derivative of L with respect to y set equals to 0 gives us equations 2. Similarly, partial derivative of L with respect to z set equals to 0 gives us equation 3. Similarly, partial derivative of L with respect to lambda set equals to 0 gives you this constraint curve, equation 4. So now our goal is to solve this system of equations and find the value of x, y, and z. Again, we don't care the lambda value. Solving first and second, same lambda, equate 1 over x equals to 1 over y. This implies y equals to x. Equation A. Solving first and third, again same lambda, equate 1 over x equals to 1 over 2z. This gives z equals to x over 2. Equation B. Then substitute those values of equations A and equations B into equations IV. Then equation IV reduces to x is square plus y is x. So again x is square plus z is x over 2 square equals to 9. Solve for x. This gives us x equals to plus minus 2. Since y equals to x, so y is also plus minus 2. Then z equals to x over 2, so z equals to plus minus 1. So we found the critical point 2, 2, 1 and minus 2, minus 2, minus 1. 2 critical points. So the next step, evaluate the functions at those critical points. We found here f at 2, 2, 1 is 9 maximum, and f at minus 2, minus 2, minus 1 is minus 9, a minimum. I hope this answer makes sense to you all. Quick remark, we can also solve the shortest distance types problems. We did these types of problem in section 14.7, but this time using Lagrange multipliers, means using lambda. Let's do the example 4. Let's revisit the shortest distance problem that we did in section 14.7. So the question was, find the shortest distance from the point P to the plane. The plane is x plus y minus z equals to 1. So begin the solutions. So let d be the distance from given point P to any arbitrary point Q on the plane. Then our d equals to this equation star. This is just the distance formula. Since any point minimizing d square also minimize d, so we now minimize d square. So d square equals to, just get rid of this radical, we have these equations. So the mathematical setup for Lagrange method is, we are minimizing because we are finding the shortest distance. So we want to minimize. So minimize the functions f, which is d square. That means x minus 2 outside is square plus y square plus z plus 1 outside is square, subject to constraint. Those x, y, z should satisfy this equation of plane. X plus y minus z equals to 1. Then just follow the routine computations, means define the Lagrangian functions. So Lagrangian functions L x, y, z lambda equals to objective functions minus lambda times the constraint. Then I'm only giving you the hint here because this example we did in 14.7, and also the idea for a function of these three variables we did in example 3 here. So now exactly follow this routine computations. Find Lx, find Ly, find Lz, find L lambda, set them equals to 0. Then we have 4 equations, that's the system, and find the value of x, y, and z. Solving that systems, it gives us the point x, y, z, that's the critical point, 4/3 minus 2/3 minus 1/3. Therefore, the shortest distance is x minus 2 square, y square, z plus 1 square. That's the star equations here. Oh, there are 2 stars here, so I may need to put this as double star. I'm talking this star this time. Then we know x equals to 4/3, y equals to minus 2/3, z equals to minus 1/3, and simplify, it gives us 2/3, approximately 1.15. This is the exactly same answer we got in previous sections using other methods. Great. So we finished these sections as well as we finished chapter 14. Thank you.